This video is intended to help you with the homework for 6.3 in Hurley. As you probably recall, in 6.2, you learned the truth tables for the logical operators, and you use those to calculate the truth value of statements where you knew the truth value of the simple propositions in the statement. In 6.3, you're going to learn how to make a full truth table, and you'll use that to classify statements where you don't know the truth value of any or all of the simple propositions, and you'll also use it to classify or compare statements. So at the beginning, Hurley gives you a formula for determining how many rows you need in your truth table. And basically, you just need enough rows to represent all the possible combinations of truth and false that you could have. For practical purposes, these are the three truth tables you're going to see and do, because we won't do anything more than 3 letters. So if you have one letter in your statement, you just need the case where it's true or the case where that letter is false. If you have 2 propositions or 2 letters in your statement, then you have to represent the 4 possible truth and false combinations. And then if you have 3 letters, you're going to have 8 rows, and that will give you, that will help you represent the possible combinations. Here you would have 4 true, 4 false, 2 true, 2 false, and then true, false, true, false. And if you just stick to these, that will give you all the combinations that you need. So the first thing you're going to do is you'll have a single statement that you'll classify as tautologous, which means that under the main operator, you have all truths or all T's. Self-contradictory, under the main operator, they're all false. And contingent statements are cases in which you have at least one, under the main operator, there's at least one case in which it's true and one case in which it's false. And Hurley defines these fully in the book. And then when you compare statements, they can be logically equivalent, which means they have the same truth value in each line. Contradictory statements have opposite truth values on each line. Consistent statements have at least one line in which both are true, and inconsistent have no lines in which the truth values are both true. Now, you can have some overlap between this classification and this one, so you're always looking for this is a stronger relationship to be logically equivalent or contradictory. And so you first want to see if they fit one of these, and then you would go on, if they don't, and classify them as either consistent or inconsistent. And in fact, just looking at logically equivalent statements, once you're done with this section, you can go back to that De Morgan's rule, and you can look at the statements that are logically equivalent, and you can use a truth table to show it. Okay, so what I'm going to do here is just demonstrate the different cases in which you would classify statements. So here you have the case in which R and not R, you have one letter. So you only need to represent the case in which R is true and R is false. And we can put that here. I didn't need that line, sorry. So you have the case in which R is true and R is false. When R is true, not R will be false. And when R is false, not R will be true. And now the last thing we do is the conjunction. So you have true and false. If you look at your truth table for conjunction, true and false is always false, and false and true is always false, right? The only case in which a conjunction is true is when the conjuncts are both true. So this one would be classified as self-contradictory. And then in this case, you have the main operator we want to figure out is the horseshoe here. Remember, that's the operator that has scope over the entire statement. So we're going to figure out the left side first and then the right side. We don't really have to do anything there. Now, Hurley shows you 2 different ways to do the truth table, and you can do them however you want, whatever makes sense to you. And in some cases, it's just easier to do it one way or another. So in this case, we have 2 letters, so we need the 4 combinations, and I'm just going to put them right under the letters. So we'll use R is true, true, false, false, and then S will do true, false, And then I'm just going to go ahead and repeat it over here to make it easier to read. Okay, so that would be, I haven't done any using the logical operators, I'm just making the truth table itself. So here now we would look at the truth table for the horseshoe. And if you remember, or if you're reading it, we know that the horseshoe, the conditional, is only false when the left side is true, the antecedent is true, and the consequent is false. So I'm going to put that right in there. And the rest are true. And then now we can do this conjunction. So we have true and true is true. False and true is false. True and false is false. And true and false is false. So that's what we have on the left side in the antecedent. And then we can do the main operator here. So true and true is true. False, horseshoe false is true. Be careful there. A lot of students will make that false, but that one's true. False horseshoe true, again, is true. And false horseshoe false is true. Okay? So this statement is tautologous. Okay? And then let's take a look at the third one. Once again, we have 2 letters, so we just need 4 rows in our truth table. So we'll do true, true, false, false, true, false, true, false. This one would be true, false, and true, true, false, false. So make sure you're consistent there. When I assign N, true, true, false, false, I was consistent there. Okay, so the first thing we'll do, the main operator in this case is once again this horseshoe. So we have to figure out, on this side it would be this horseshoe. So we want to negate N and do the disjunction and then the conditional. So we end up with false, false, true, true. I'm going to cross those out. Okay, so I just negated N, and now I'm going to do the disjunction. And the disjunction is only false when both are false. So this is true, false, true, true. And then I'll go ahead and just cross those out so I can see it. So now we just have to do this conditional before we can do the main operator. And again, for the horseshoe, it's only false when the left is true and the right is false. So that's this case here. And then the rest are true. Okay. And now the last thing is, again, the conditional. We have true horseshoe true is true. True horseshoe true is true. True horseshoe false is false. And false horseshoe false is true. So this statement is contingent. And then the last one, for this one, I thought it would be easier just to set up the full truth table on this side, and then I'll just look over here to do the bigger statements. So the main operator is this horseshoe. So that means I have to do each side of this, and then the last thing we'll do is this column here. And we don't have to do anything with P, but before we can do this horseshoe, we have to do the smaller one. So let's see, we have Q horseshoe R, so true horseshoe true is true, true false is false, false true, false false is true, and then true false, true, true. So now we'll just do P and then the result of this. True and true is true, true horseshoe false, false, true, true. And then since we have false on this side, all of these are going to be true, right? Because anytime the antecedent is false, the conditional itself is true. Okay, so that's what we get here. And then we have to do these 2 conditionals. So we have true horseshoe true, we have true, true, true horseshoe false is false, false again. And then once again, the left side is false, so all of these are going to be true. And then P horseshoe R, we have true, true horseshoe, T horseshoe, T and T is true, true horseshoe false is false, true, false. And then once again, all of these are going to be true. And now we'll do this conditional, and then we'll have this last one. So true horseshoe, false is false. These are true. And then the rest of these down here are true. And now we can do the main operator here. So this was the result on the left side. This was the last one we did. And then we want to compare it with this column and use the truth table for the horseshoe. Okay, so true horseshoe, true is true. False horseshoe, false is true. True horseshoe, true is true. Once again, true. And then all of these down here are true, and these are all true, and we know true horseshoe, true is true. So this is the column we need to look at, and once again, this one is tautologous. So that means a tautologous statement, again, is one in which no matter what truth combination of truth values you have, the entire statement is true. Okay, so that should give you a good idea of how to do 1, 2, or 3 letters, which is the most that you will have. And then the other exercise that you have to do, I'm not going to do it again, is in the second part, they give you pairs of statements, and you're going to do the truth table for the pairs, and then you're going to compare their main operator column. If they're exactly the same, the statements are logically equivalent. If they always have different truth values under the main operator, they are contradictory. And remember, you want to check those first, and then if they aren't logically equivalent or contradictory, go on to label them consistent or inconsistent. Consistent has one line in which both are true, and inconsistent statements, there are no lines in which both of them are true.